we'll do this problem number 9, where the airplane is taking off at this point 327. So in my vector form, it's the first point from the center of the universe to a point on the line. Then we have the direction vector, 3, 4, 10. And then we multiply by t because speed times time equals distance, and we're adding distance and distance to get distance. Then to calculate the speed, we just take that blue vector and take the square root of 3 squared, 4 squared, and 10 squared added together. That's the magnitude of the velocity vector, and you're going to get square root of 125 meters per minute. Now, a second airplane is moving, leaving at the same time, and it's leaving the point negative 523. So that's that first starting position, and then you're going to 316.39. So if you take there's the start, and if you take AB, vector AB, the head is B and the tail is A. So if you subtract those, you get 8, 6, 16. Now it looks a little off because 4, 3, 8 is supposed to be my direction vector, but 8, 6, 16 is in 2 minutes. So if you divide by 2, you're going to get the 4, 3, 8. And that starting position negative 5, 10, 23 to the direction vector 4, 3, 8 is that second model airplane direction. Now what we're going to do is we're going to see where they meet. So I'm going to take the 2, like I have here, and then we're going to make them into parametrics. So we just add a cross here. And so the first x will be equal to 3 plus 3t. And then y will be equal to 2 plus 4t. Z is going to be equal to 7 plus 10t. Double check my numbers there, 3, 2, 7, 3, 4, 10. Good. Now, when you do this one, the second one, I would give this t a different variable name. Maybe call it T2, like Terminator 1, Terminator 2. So then you've got x is equal to negative 5 plus 4 T2. And then y is equal to 10 plus 3 T2. And z is equal to 23 plus 8 T2. Notice that the steps, the lambda and the mu's, or the T1, T2 are different because now, what are you going to do to find the intersection point? Here's the good part. What do you do? Set them equal. X equal to x. Y equal to y. So you do that, and you're going to get 3 plus 3t1 is equal to negative 5 plus 4t2. What do you think, Ella? Is that logical? And so we're going to do that with y, and then we'll solve for t1 and t2. So y is going to be 2 plus 4t1 equal to 10 plus 3t2. And then when you put these two together, like this, we should be able to solve for T1 and T2. Let's just do a quick little simplification here. I'm going to add 5 to both sides. So I get 8 plus 3T1 equals 4T2. And I'm going to subtract 10. I'm going to get negative 8 plus 4T1 equals 3T2. Now, I'm sorry that you're going to have to do this, but you're going to have a little bit of a challenge getting these to cancel out. You're either going to have to multiply by 4 and negative 3 or negative 4 and 3. So it doesn't matter which one you want to get rid of. Let's get rid of these. So I'm going to go negative 4 And then I'm going to multiply these by 3. So what happens, you'll get negative 32 minus 24. What's negative 32 minus 24? Negative 56. And then negative 12 plus 12 is 0. And then negative 16 plus 9. Negative 16 plus 9 is what? Negative 7 T2. So then you're going to get T2 is negative 56 over negative 7, and I get T2 equal to 8. So if T2 is 8, now we can find T1. You don't need to, but let's say we did. T1 is going to be 8 plus 3T1 equals 4 times 8. So 3T1 equals 32 minus 8. 3T1 equals, what is that, 24? So what's T2? Is that right? T1 also equal to 8? Is that right? That's weird. That's weird. So there, what does that tell you if those times are the same? Yeah, yep. And so find the position of Q. So just put 8 into any one of them. Let's do it this one. X, Y, Z is going to be negative 5, 10, 23 plus 8 times 4, 3, 8. So negative 5 plus 32. 32 minus 5 is 27. 24 and 10 is 34. And 23 and 8 is 31. So I get the intersection point, Q, to be 27, 34, 31. Did anybody get that? Okay, feeling good about it then. Good. 64 and 23, so it'll be 87. 87? Thing. Last thing we have is find the angle theta between the paths of the two. So to find the angle between them, the formula looks like this. Cosine theta equals A dot B over magnitude of A, magnitude of B. You could memorize that, but you don't have to. But what you do need to know is which part of these, and I'm going to give the green one here and the blue one here. The greens or the blues are the directions. Which are the direction vectors of these airplanes? The green or the blue? The green. So we're going to call this green here, we're going to call, wait, did you say green? Green is the position. That's center of the universe to a point. That's not going to tell you where the plane is flying. It's the blue is going to be in the direction. And we're going to call this vector A and this one vector B. So when you put those direction vectors in, 3, 4, 10, dot 4, 3, 8. Then you take the magnitude of 9 plus 16 plus 100 times 16 plus 9 plus 64. Cosine of theta is going to be, now we multiply across here. Multiply these and then add them up. So you're going to get 12 plus 12 plus 80 over the square root of 125, which we've seen before, and 64 and 16 is 89, square root of 89. So would you tell me what 104 over the square root of 125 over the square root of 89. What is that decimal? It should be between 0, -1, and 1. Hopefully it's going to be positive, so it'll be between 0 and 1. Get me a decimal for good. All right, so when we calculate 104 over square root of 125 divided by square root of 89, I get this. Now do inverse cosine of 0.9860. And what do you get? 9.598 or 9.6 degrees. And we're going to see if you're right. Do you think you're right? I think you're right. The airplane out of here. This is going to work. I know it. And square root of 125, got all that, got all that. Oh no, where is it? Thought I had it. I think there must be another one up here. Here? Doesn't look like it. I know it's 10 degrees, 9.6 is correct. And that's it for the airplane problem.